Are we good to go?
You're good to start. I just need to find the TV remote.
Oh, does anybody see it? So, I think most of you are aware that the difference between physics and engineering is that physics tends to be the theory and engineering tends to be the application. Occasionally, you get a situation where there's one foot in each camp. And psychometrics is one of those situations. It is one of my favorite subjects. We're all a little twisted. I'm twisted in the direction of liking psychometrics. It is the study of air-vapor mixtures. And air conditioning is applications to air-vapor mixtures. You probably all know this, but when you run something through a cooling coil, you don't just cool the temperature of the air, you also remove moisture. And so what you've done is you've altered that air-vapor mixture to not only be colder, but generally to have less moisture in it. All of that is predictable. It can be calculated. You can select systems and equipment to do anything along those lines. It all starts with a psychometric chart. Now, back in the day, we would have one of these plasticized charts, and we would have pencil, eraser, ruler, and everything was done on here. I grew up in an analog world, and I would submit we still live in an analog world. We don't live in a digital world, but we have converted much of the analog functions in our lives to a digital kind of a basis because that's the hardware that we've got that lets us do more stuff. So that's good. But when you get so digital that you don't know, forget, never learned the analog thing it was based on, then you get into one of those scenarios where garbage in equals garbage out. And so the important part is understanding the basis of it, and that's kind of what we're going to try to accomplish over the next 2 sessions, okay? When you're using software to do what I grew up doing with this chart, and there's nothing wrong with using the software, usually the software will give you the option of not only, getting your whole thing and giving you the answer you're looking for, but it will also give you a picture, any of the good software, of the chart and show where the air went and what happened on the chart. I'm going to submit that you should be in the habit of having it do that if you're using the psychometric software. You may plug in the numbers you want, you may get the output numbers that you were looking for, but you should always look at it on the chart. That should just be a base habit, because occasionally you'll get stuff that doesn't make sense. And that's when understanding what it was based on in the first place is important. Okay. So I also handed out a little copy. This is just a blow up of one part of my little carrier cheat sheet I use. Look how they spelled. Yeah. What is the plural of formula? So if you Google that, what it will tell you is that the older school, higher scientific, coming from Latin plural, is formulae, as you see it on your little sheet there. Today, in math, if you're studying, if you're a math major, you're going to be accustomed to saying formulas with an S on the end. If you're a scientist, you're going to be more accustomed to saying what's here. The reason I bring that up is that in 1911, Dr. Carrier published rational psychometric formulae. There wasn't just one formula. And there are three on this that we might get to today, and if we don't, we'll get to them next session. And that's if you go down to the 5th, 6th, and 7th. Did I count right? Yeah. You'll see sensible heat, latent heat, and total heat formulas. Those, combined with your psychometric chart and a load estimate, which I refuse to talk about because it bores me to tears, so when we do load estimating, probably I'll suck Brian into doing that. But the combination of the load estimate, which is telling you what's the total cooling we need, you know, in each space, and then you tell it how many degrees cooler the air is going to be, and that then backs into how many CFM do we need at what temperature, right? Which then gets married up with this for the equipment selection and part of the load estimate. And then those three equations. Okay, that is everything you need to decide how much cooling you need, mess with options, pick equipment, size pipes and ducts, or have the information you need to then size the pipe and the duct. Actually, you don't size the pipe and the duct that way, you then take it another step. But you know how many CFM or how many GPM or whatever it is that you're sizing the pipe and the duct for. Those are the fundamentals of our whole industry, and it's all based on the site chart. So we'll start with just building a site chart. Eventually we'll get into Dr. Carrier was one of those geniuses that could take theory and put it into a practical application. And he had three, at least in my view, three major realizations that nobody before him had had. And I don't know how, you know, if you've ever tried to untangle a ball of yarn, especially after your cat's been messing with it, it's pretty hard to do, right? I don't know exactly of those three major things which one occurred to him first or how, but what came out of his 1911 rational psychometric formulae was not only the theoretical basis of it, but the equations and the chart. You don't have to know the derivation of all those, it's a hell of a derivation. You don't have to know that to use the chart. You just have to know what the chart does. Taking it from a theoretical level that nobody else had grasped and putting it to a chart level that anybody can use, at least if they learn how to use it, right, was a dramatic thing. And it was published, like I say, in 1911. You could pretty much divide our industry into before 1911 and after 1911, because after 1911, there was a basis for design. By the 20s, nobody was building a movie theater anymore that wasn't air conditioned. That was one of the very first mass applications. Because the theater owners, I said movie theater, but live theater, you know, any kind of a theater, they knew that they would sell tickets in the hot part of the day when they'd never been able to do it before. Theater performances were always at night, late in the summer, because that's when it was cool, or cooler. Now, they could make the theater cooler. People would actually come see stuff during the day, which was a whole new thing. So, if you look down Hollywood Boulevard, and you look at Pantages, and the Chinese Theater, and there's a whole line of them. They were all built in the 20s. And they were built because they could be air conditioned. And because they could be air conditioned, they were a viable business opportunity. Now, this whole thing has then just gone on from there. So that's the upfront. Now let's build a psychometric chart. Let's start by finding a pen that works. As you know from experience, that's sometimes the hard part. Okay. Across the bottom of a site chart, and you've got one to look at, what's the bottom, the x-axis there on your chart?
Dry bulb.
Dry bulb, yep. Dry bulb temperature. Now, the one that you've got there is for standard temperatures, and it runs from what to what, from left to right?
20 to 110
20 to 110. There's a high temperature one,
with 5. Yeah,
or 105, yeah. There's a high temperature version that just continues that on, because obviously, how the hell would you use this in Palm Springs? You know, the design temperature in Palm Springs is what? It's gotta be at least 120, maybe 125. So, there are others, and there's a low temperature version as well. But this is the one we spend most of our time on, and this works for anything you're designing in the LA Basin. 105. Okay, up the side is what?
grains of moisture.
What do they call grains of moisture? Grains of moisture is the terms, but what? No, I'm waiting.
Humidity ratio?
No. Surely it's written on there. I don't know, let me look. That doesn't say, does it? The grains of moisture is the way you express specific humidity. Why do we call that specific? Because it is what it is. It's an exact number. There are 7,000 grains in a pound. That's dividing a pound up into some pretty small pieces, isn't it? But when you're talking about moisture in the air, and the air is mostly gas and not very much moisture, you're dealing with grains. Now, next thing we'll draw up here. What is this? There's two proper names for it. What is it? Dew point line, I heard that, yeah. That's one of the names. What's the other name that would be proper?
Wet hole.
Saturation line. So let's talk for a moment about why those are the same. No, let's talk about the next thing first. What is relative humidity? It's a ratio. It's a ratio of what? What is it a ratio of?
Air, I mean, not.
Moisture in the air.
Grains of moisture.
Moisture in the air compared to what?
Saturation.
Okay, compared to saturation, but what's another way of saying that? It's a ratio of moisture in the air compared to
How much moisture the air can hold.
how much it can hold, which would be saturation, right? So, if this is 100% saturated, then some line here in the middle, if I, just by eye, that would be like 50%, right? Half of it? And sure enough, if you look at your psych chart, you will see a 50% line, and you'll see basically a line every 10%, right? And the point of this is to tell you, really, how much moisture is in the air and how much more would it hold. Now, what does the saturation point have to do with the dew point? Come on, somebody struggle with something here.
What is
Dew
the
point is where our temperature rise, it's where we're phase changing, we're directly seeing moisture forming because the air can't hold any more moisture in it.
That's a good way to put it. We're seeing moisture forming because the air can't hold anymore. And the surface that it's up against is colder than the saturation temperature. Now, wet bulb is a field determined thing. This is called a swing psychrometer. Psychrometer, like psychometrics. You'll see I've got one temperature bulb that looks like a regular old temperature bulb. And the other one's got a little cotton sock on it. There are two ways of determining whether you've reached saturation. The super expensive laboratory grade, get it right every time method is you build this chamber with sprays and a fan, and you blow the air through all these sprays until by the time it leaves, the air is fully saturated. We can't carry something like that around with us and use it. Could you use it for, you know, maybe some really precise equipment calibration purposes or something like that? Sure. But we're not going to use that. That's using a saturator. Nana Ansari refers to this as the wet wick method because this little cotton thing, which, by the way, when you unscrew this, you've got the rest of the wick hidden away in there. Not only does that hold moisture, but when this little wick thing eventually just frays away to nothing, you snip it and you try to fit on some more if there's still enough flex in your cotton to make it work. And so what you do, nobody would ever admit to spitting on this, so I won't tell you that anybody's ever done that. So you bring your water that you brought handy for the purpose. You get it nice and wet. And then you do this. And you do this for a while. Now what's happening in that wick while I'm doing this? Water's evaporating, that's exactly right. And what happens then to the temperature on the surface of that thermometer bulb while the water's evaporating? Remember that during phase change, the moisture, yes sir?
I'm sorry to interrupt, but I have a question.
Yeah.
Are you guys still using this device in the field along with your abacus? Or is there a different way that you do this now?
There are digital tools in the analog world which will do that. This is the analog method, all right? There was a purpose. I knew some smart ass would come up with something along the way. So, while I'm doing this and evaporation's taking place, what is evaporation? I mean, that's the liquid changing state to a vapor, right? That's what evaporation is. Well, remember we had, I don't remember, 742 or some number of BTUs per pound that gets released, or excuse me, that has to be absorbed by the water to turn it to a vapor. Well, where, as I'm doing this, and it's turning to vapor because it's evaporating, where's it pulling the heat from to do that phase change?
The air.
Part of it's the air, but also it's pulling it from the thermometer bulb. It's cooling the thermometer bulb, isn't it? Because it's drawing heat from the thermometer bulb to turn it into vapor. Thank you. Now, when I stop looking at this, I have to look really fast. Because as soon as I stop spinning this thing, the temperature, which has gone down, 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 down until it's hit saturation, because it will eventually hit saturation. It probably does it within 30 seconds or at most a minute of when I started doing this. And I've been doing this for what, 3-4 minutes now. It's there. But as soon as I stop spinning, you can just watch the temperature go back up on the bulb toward ambient. So I pull this off, and what I'm seeing is 71 wet bulb and 75 dry bulb. Now, is this precise? Not particularly. I mean, I'm eyeballing the little degrees on the thermometer bulb. One of the very first things you learn in engineering school is the difference between precision and accuracy. You can have 17 digits of precision in the number that comes out on your digital tool that gave you the number, but is it accurate to 17 digits? Never. This is just as accurate as the digital tool. I would submit it's more accurate because this doesn't get out of calibration. But is it as precise? No. You're doing really good to get it within a half a degree looking at the little, the little gradations on the thermometer. But what I will tell you is, who cares? So I was getting 71. Now, just out of curiosity, I'll look at it again. And if I look at it now after it's been sitting still, it's up to 74. So that's how, you know, it'll change really quickly. We've got numbers across the bottom here, don't we?
Yes.
Do those numbers continue up and hit the saturation line? They do, don't they?
Yes.
Okay, so what else is here? The concept of wet bulb has been known for had been known for a couple hundred years before Dr. Carrier did his thing in the early 1900s. Wet bulb was not a new concept. And so that was not one of his three big realizations that he had. We knew what wet bulb was. After the realizations, when Dr. Carrier put together the psych chart, he wrote the wet bulb nut lines to do this. And if you look along here, along the saturation point, and you just pick out any spot you want, you'll see a wet bulb line like that. Do you guys see it?
Yes.
Okay. In addition to the wet bulb, you'll also see a little scale up here labeled H. What is that? Enthalpy. Enthalpy is the total heat content. And you'll notice if you study your chart that the enthalpy lines and the wet bulb lines are the same. Am I to the point where I can talk? No, we have a couple examples to make sure that we have drilled this into your head. So let's look at air at 75 and 60 grains. Make a dot, mentally at least. Okay? Bing. Okay? How do we find the dew point? So let's talk about the weather for a minute. Unless a new front comes in bringing in more moisture, or it's Santa Ana, it's bringing in air that's drier. Unless you have some new front coming in, if you walk out and you get in your car to come to work and it's 75 and 60 grains, and then you come out, you're going to take a walk about 10 o'clock, you know, and stretch your legs. And now it's 85. How many grains will be in the air? Assuming no weather front change.
So the 60 grains.
There's still 60 grains. It hasn't changed. So now you're going to be here. The specific humidity is constant unless you bring some more moisture in or you take some moisture out. If we get a Santa Ana, it takes moisture out because new air comes in that's drier and it displaces the air that was at 60 grains. And now maybe you got air that's at 35 grains. Or we got, like we did that super humid day earlier this week that we had, where it was cloudy for much of the day and the air was coming in from the Sea of Cortez and it blew out our air and it brought in air that was much more humid. Okay, so if you've got a weather change, you know, if a front change and you change the moisture, it'll change. But on a day where there's nothing special happening wind-wise, this is going to be constant. What is the dew point?
It's like 53.
Like 53. Very good.
Or
Yeah, 53.
Okay? So now we know the dew point. We know it was 75 and 60 grains. We started there, right? Okay. Let me ask you a question. If this is the dew point, and we run a duct through here that's not insulated, and it's got 55-degree air in there, will it sweat?
Yeah. Or no, not
Is that hotter than the dew point?
yeah.
Short answer is no.
No.
Because if I got a 55-degree duct in a space with a 53-degree dew point, it won't condense. We're above the dew point. What if we were making 50-degree air?
Yes.
Yes, now it will. And if we were making 53-degree air in a duct in a 53-degree dew point room, we'd probably have just a little bit starting to show, a little bit of dew on the outside of the duct. This assuming it's not insulated, right? Or a pipe. You get into this a lot with pipes. Let me ask you a question. How often do we insulate condensate drain lines?
Not often.
Not often is the right answer. Now, if this is within a conditioned space, it's probably not a big deal. Probably the condensate, which is cold, right? It just came off of a cooling coil. And if everything's working right, it hits the drain pan and it goes to the drain line, and it's kind of warming as it goes. But as it goes down that drain line, it's still pretty cold. But in a conditioned space, you're probably fine. What if you have an uninsulated attic and that's where your condensate drain lines are? You better be insulating those lines, because every one of them will sweat. You'll be fortunate if the bottom of the drain pan of the unit isn't sweating. In theory, those drain pans are supposed to be insulated, but cheapy little fan coils, probably not. If you're going to put equipment in an attic that's not conditioned, even if it's ventilated. If it's ventilated, you know how it is with attics that are ventilated, they're still hotter than it is outside, you know, by the end of the day. I can almost guarantee you it's going to sweat. And it's the same principle that we've been talking about with all this other stuff, right? It's the dew point versus what's the temperature. And the dew point in that attic, let's just pick a number. Let's say that your attic temperature is 90 degrees and about 80% relative humidity. What's the dew point? I haven't looked this one up, so I don't have my crib notes. One of you guys are going to have to tell me. 90 and 80% relative humidity.
Like 70 or 79, 78.
Okay. I will guarantee you there will be times when the condensate drain line will be colder than 78 or 79 degrees.
Like always.
Like always. Yes. Okay. Now you're hearing about warranty calls we've had over the years. You've also heard about things we fixed that other people did wrong. Okay. What else do I have? Let me give you another example. This 75 and 60, no. Give you a different one. So let's say we designed this thing surgery suite. This is really common. Let's say we took a surgery suite and we designed it to be, let's talk about surgery suites for a minute. There's a code requirement for those. You have to maintain, they don't care what temperature it is. Temperature's irrelevant. But you have to be between 20 and 60% relative humidity. The basis of that is that if you're drier than 20% relative humidity, the wound edges will dry out and it won't heal properly after it's stitched up or stuck together or whatever you're doing. The reason for the 60% is when you're above that, you are now at risk of a bacteria situation. Okay? So it's an infection control. So 20 to 60, and this is rigid. This is rigid. I think I told you guys at some point in the past that the state of California started, instead of inspecting every 3 years, like 15, 20 years ago, they started they give you a call and 45 minutes later they show up. Have you gone through that? Yes, I'm seeing some nods. One of the things they look at as soon as they show up is take me to your operating room. What's the relative humidity in there? So they do monitor that now. You will not find a charge nurse on a surgery suite floor that is not looking at relative humidity. So let's talk about what that means in the real world. Most of these rooms were designed for something like 70 degrees and 50% relative humidity. There is not a surgeon out there above the age of 30, 35, who runs an operating room at 70 degrees. They whine and cry like little babies 64 is like the highest temperature they want to see. Now, there's a reason for that. We converted from these sodium vapor, hot lights. You guys have all seen pictures of ORs if you've never been in one. And there was all these lights over the shoulder of the surgeon so he could see what he's doing. Those lights used to be the monster heat load in an OR. And there's still some of them out there, but most of it, it's an expensive conversion. Most of them have been converted to LED. But it's like 20 grand per OR, per room, to convert to LED, so that's why there's still some of them, especially in the lower budget hospitals, that haven't been converted, okay? And the LED's just as good, but it's a big upfront cost. What's different is the heat load. These surgeons had lamps right behind them, putting out massive amounts of radiant heat. And so they would crank the room down as low as they could get because they didn't want to be sweating all over everything. And you know, some of those guys wear glasses. And so they got glasses. Some kinds of surgery on top of that require, you know, a face shield or some kind of other. So they're in there sweating and the glasses are fogging up and all this. So that's why there's a legitimate reason why they wanted it to be cool. There is no such reason in an LED room, but if you spent the first 20 years of your surgery career doing that, then you want to keep it that way because you're a human being and all human beings hate changing. Now there's 2 and sometimes 3 layers of people around an operating table. So you got the surgeon and probably not even the anesthesiologist, you know, whoever the surgery nurse was, are in that first row around the table. And then there's another row of people doing less critical things. And there might even be somebody else in the third row. The second and third row people are wearing mukluks. They look like Eskimos because it's so cold in that room. But who drives the bus in an OR? The surgeon. So, now that I've explained reality, because that is reality, if we start at 70 and 50%, but instead, we choose we're going to run that room at 64. Remember, the specific humidity hasn't changed. So we come over here to 64. What's our relative humidity now?
I thought you said it was still.
Specific is still the same. 55. Yeah, 65.
It's probably a nose over 60, isn't it? And what did I tell you was the hard and fast #1 thing being monitored in that room? We don't care about temperature. The compliance things to monitor is what? Relative humidity. And 60% is the absolute top. And if you take a room that was designed for 70 and 50% relative humidity and you just operate it normal and then somebody goes in and they turn the temperature sensor control down to 64, you are now over 60% relative humidity. And this is how every operating room in Los Angeles, California, and probably the entire state of California was operated when this 20 to 60 thing became code. You remember when that was? Long time.
I'm still freaking about not saying C because that's something.
Okay. So, yeah, in the Gulf of America. Anyway.
Wrong body of water.
I
You don't know your geography.
don't have to know geography.
Yes, you do.
Okay. The Sea of Baja.
Okay, I'll buy that.
So, now what we've got is a room that was designed for a condition and people want to operate it at another condition. And psychometrics tells you what will happen if they do that. The solution is you have to basically change your design parameters. And we reverse engineered that many times in many ORs over the last 15 years to where, okay, since 70 and 50% isn't where they're going to run it, and I've got to end up probably around 64, and I got to be under 60%, what's my new design criteria? And then you end up probably saying that it's now going to be about maybe 67 and 50, or maybe you even shoot for 64 if you can do it. We've had the Curlin Job Surgery Center as a customer since we built the building in '97. And you may not have heard of Curlin or Job, but Frank Job invented Tommy John surgery. And Curlin Job has been the #1, without question, athlete surgery center for pretty much any sport you want to take. If you're over there visiting and you're standing in the lobby, I remember Lisa Leslie walking by me and she was wearing a crop top, and I swear her belly button was almost up to my nose. You know, you see tall people, short people, big people. This exact situation happened there. Matt Calabrese did a retrofit maybe 4 years ago, something like that. It was after COVID. And instead of the original screw chillers that were designed to make 42-degree water, he put in a dedicated air-cooled chiller for just the surgery center air handling unit that would go to 38. Now, when you go to 38-degree water, you're going to have glycol, you're going to have some other things because you are concerned about the suction temperature being down around freezing. But with 38-degree fluid going through the existing cooling coil, now suddenly we're making a lot colder air. Right? 38 instead of 42, it's pretty obvious. And that resolved this. And now, instead of us at 64 bumping 60%, we're more like about 55%. So we've got a little margin there. Kaiser, if I understand it correctly, and talking to Travis English, has standardized. They will never again do a building that doesn't have 38-degree water going to an OR. And this is why. Okay? But all this comes from psychometrics. But what did I have next? Hey, you guys know to be rude and raise your hand, yell at me, and whatever else at any point, right? So, that wet bulb of 75 and 60 grains, excuse me, the dry bulb of 75 with 60 grains, what's the wet bulb? One and a half is close enough, yeah. So, how many of you know what an evaporative cooler is? How many of you know what a swamp cooler is? That's the more common term. Swamp cooler is a pejorative term relating to how they start to smell if you haven't taken proper care of them. So, a swamp cooler is kind of like that saturation lab box I was talking about. You set it up, typically you've got a box, you got a fan that's usually blowing down, but it could also be a side discharge if you want. You've got probably on 3 sides of this thing, you've got pads, about this thick, woven fiber, heavy fiberglass. And you've got a little condensate, you've got a sump in the bottom, you've got a little condensate pump that takes the water in the sump and has the little black polypropylene hose just like you see people using in drip sprinkler systems. And it's dripping water all across the top of the pad so that the pad's fully wet. And you've got a water line coming over here and you've got a toilet float there with a valve to keep the water level where you want it. And this is 100% outside air. This fan is blowing down and it's sucking air in through 3 sides where you've got your pads. The way that works is it starts off at our, we said 75, 50%, and this was 61 and a half, right? The water follows the air temperature follows the wet bulb line. And so it creeps up this direction. It's trying to get to saturation, right? Because we've got it going through this wall of fiberglass that's all wet. And so it becomes more and more saturated. Do you think that with a swamp cooler we'd get all the way to full saturation? If it's brand new, like, there's some variables. For one thing, how much air are we putting through here? What's the velocity through here? If we're screaming all the air it can do, we don't manage to evaporate as much, or, you know, get as far up that temperature line as if we were running this really slow. Because if we're running it really slow, there's more exposure to the water, and it gets a little further up there. So the velocity, the total CFM we're delivering is a variable here. But typically, a swamp cooler will do somewhere between 70 and 80% efficiency. In other words, you'll get 70 or 80% of the way to saturation, which means if you just took your ruler and you measured this line right on the chart, and you measured 75% of the distance, if it was 75% efficient, according to the catalog, you would know now, here's the new spot. Another way, if you knew the efficiency, is you would take this temperature, 75, and that one, 61.5, and you'd say, okay, what's the difference? What's 71 minus 61.5?
13.5. 13.5.
Okay. And if you knew that it was 75%, you'd take 3/4 of that and subtract it, and now it's going to be 53 plus whatever 3/4 of 13.5 is. And so you're probably making air,
63.
yeah, somewhere in the low mid-60s. Now, as this gets older, the fiberglass starts to have mineral crap evaporate and, you know, form on it, because that's going to happen, right? There's minerals in the water. All these other things happen. Get a little bit of algae growing in there, whatever it is. Maybe part of a Vaughn's bag gets stuck. What happens to the efficiency?
Decreases.
Yeah, it decreases. So, it's, you know, when it's brand new, you turn it on, it would have got to 63 or whatever. But as it scums up, gets older, gums up, et cetera, et cetera, et cetera, now instead of 63, you're making 64, 65, 68. Where do you see these in a commercial application? I heard somebody say restaurants. You all know that they've got a fume hood, right? They'll have an oven hood, and that oven hood is exhausting over the top of your cooktop, right? How do you get makeup air back into the building? Separate system, right? Because that hood over the cooktop is just taking air out, but you got to replace that air somehow. And so typically, what they do is they use this, and that's getting them some sensible cooling at the same time, because it's cooling the outside air down. Back before climate change, when it was drier here, and when everybody had swamp coolers in Moreno Valley and 29 Palms, you would see these did a pretty good job with the restaurant. But when we hit, like we did the other day, I think I had 77 wet bulb at my house. I had 76, but it was later in the day, so it would have been 77. There will be now, in the typical year, several weeks where we're a little muggier, a little more humid, and now the restaurants, kitchens, are just brutal. Because we didn't do any dehumidifying here, did we? In fact, we added moisture to cool the air. And yeah, if it's blowing on you and it's cooler, that feels good. I'll buy that. And usually that's what they try to do. They try to blow it on the kitchen staff. So that's good. But we didn't remove any humidity. And then we hit those 1, 2, 3, maybe even 4 weeks where it's, by our standards, pretty dang humid. And now it's humid and it's hot. And those kitchens are just miserable. And every little fast food place you've ever been to has a scenario that resembles this somehow. Because the alternative is you get mechanical cooling to cool 100% outside air for the makeup air going into the kitchen. And can you just see the Edison meter spinning as you're trying to do that? But we laughingly talk about who handles which billionaire, because over time, if you've been around as long as Western Allied has been, you get sucked into being involved with a billionaire somewhere. I won't mention specific names because we always have to sign non-disclosure agreements. But it almost works out that each partner ends up stuck with a billionaire.
Mine's Rick Caruso.
There was a name. So I've got one too that I am in the process of handing off, but their kitchens are mechanically cooled air make up to the kitchen because they've got these gorgeous layouts in their house, right? Where the kitchen and the dining area are all one big blown out area. It's very cool, looks really nice, but they're not gonna have a swamp cooler doing makeup air for their kitchen hood. So you do see occasionally people doing mechanical cooling. Really high-end restaurant, you're at a Michelin place that's charging, you know, $300 to $1,000 per person and gets 2 seatings in a night. They could probably afford to mechanically cool as well. But most have that. Okay, so there's that conversation. We did the sling psychrometer. I want you to think about weather for a minute. How many of you had dew on your vehicle when you got out of your house this morning? Not many. Maybe a few, ish, maybe a little. But we back up a week or two when it was cooler. How many of you then had dew on your vehicle? I'm still getting to know. Well, then maybe you didn't have any. Where I live, I did. So, how many of you have heard of radiant cooling? If you sit, and this northern tier states know all about this, places where they get real windows. If you're sitting in a short sleeve shirt next to a window and it's 30 degrees outside, that window is cold. And you can feel it on your skin because it's sucking the heat out. We talked about radiant heat earlier where the surgeon's lights are radiating heat all over the surgeon. Well, it can go the other direction. If the surface is cold, it will be pulling heat from you. I get ice on my bird bath that's about this thick almost every winter. And the lowest temperature I've ever seen at my house is 35. You say, how do you get ice on a bird bath if it's 35 degrees outside? It's because the radiant cooling cools the bath itself, the solid item, below freezing. And then the ice starts to form, and then any crystal thing. Did you ever make a crystal deal with the sugar and the water when you were a kid? Ice works the same way. Once you get that first little piece of ice forming, it covers it. But it was this thick. And it didn't get, I don't know, maybe it hit 34, but the lowest I've ever recorded was 35. That's radiant cooling. What happens to the surface of your car if it's sitting out? The radiant cooling works on it too, doesn't it? And so, just a second. He's going to have to talk to somebody else. So the radiant cooling will often get a surface down below the dew point. And if the surface of your vehicle has gotten cooler than the dew point, you have dew on it. You're out there with a scraper on your windshield, unless you are one of these people who just uses the windshield wipers and then has a mess, right? What if on your porch you got a little roof? What if the bird bath was under the porch overhang? What would happen? What would be different then?
Less exposure to the weather.
So where's that radiant cooling source? What is it? Space. And if you're under the overhang, the radiant impact isn't there. Now you're just ambient temperature. So if you shield something from radiant, and this is true for your porch in the middle of the day, you're shielding it from radiant coming at you. And at night, you're shielding it from radiant pulling it away from you. Radiant is a significant thing. Okay.
For your bird bath example, like what if you like coated the interior of it with some sort of like composite, would it then not freeze?
The coating itself wouldn't do anything. But if you put something on there that changed the temperature profile somehow, then yeah. Obvious, so it's not obvious, I didn't say so. So this is a pottery bird bath, right? And it heats up to whatever temperature the high temperature was, and then as it gets cooler and you go into night, it cools off. And it always trails the ambient temperature somewhat. I mean, if as the day's cooling, the pottery is holding some heat, it doesn't exactly get there. Well, if you had a coating that was an insulator and it could hold some of that temperature a little longer, because we only hit the lowest, absolute lowest temperature the last couple of hours before dawn. So then you could make it a difference. Yeah, I mean, if it was an insulator, it might. But as far as just a coating, no, because it's just a function of the surface temperature of whatever it is that is exposed to the radiant coolant. Okay. So the last weather concept I want you to understand, if I use the term daily range, tell me what that means. Come on, you guys are in engineering department. What does daily range mean?
The daily range you expect, I don't know.
It's the difference between the high and the low.
Yeah.
There you go.
Right? If our high today here in Santa Fe Springs is 88, and if our low this morning was 62, our daily range is 88 minus 62, or 26 degrees. If I was in Death Valley, instead of a 26 degree daily range, would it be higher or lower?
Higher.
Higher. You know how cold it gets at night in the desert? What's different between Death Valley and here? What's different?
Elevation.
Okay. What else?
Light pollution?
I'm waiting for somebody to say how much moisture's in the air.
That was my next.
That moisture in the air is your daily range shock absorber. Because when your car starts to get dew on it this morning, or ish, it's close, but once it starts to do, what's happening there is the moisture in the air is giving up however many BTUs per pound of heat so it can change state and become water on the surface of your car. And everywhere around that we're getting dew is releasing heat to the atmosphere. That's what keeps it from getting colder. If you're in the desert, there's no moisture to speak of. And you probably don't even hit, well, you probably do eventually hit the dew point in a lot of cases. But there's not much moisture, so it's not releasing much heat. And so you get much wilder swings because there's not much moisture in the air. If we were in Corpus Christi or Galveston or Mobile or Havana, would the daily range likely be higher or lower than our 26 that we had here last night? Lower, because there's more moisture in the air. My wife and I would go walk. Well, first of all, Corpus Christi, when I lived there, in the summer, the surface temperature of the Gulf was 84 degrees. And when you would go walk and sweat, but we like to get out and walk, so we would walk before we took a shower and went to bed. In that part of the world, you shower before you go to bed. You don't shower when you get up. So we would walk before we went to bed, and it would be, pick a time, 9:30, 10, and it'd be 84 or warmer, because the water, and of course, all the air was coming off the water, right? The wind was coming off the water, so it was not going to be any colder than 84. And it would hit a high of 98, 100 in August. So 84 to 98 is a daily range of 14, right? And that's what you get in humid climates. We're where we are, and we're typically in the summer somewhere in the 20s, and the desert is typically, again, unless a weather front's going through that changes things, you're typically somewhere in the 35 to 40 degree range. That's relevant because when you're designing an air conditioning system, and it's going to be for a 24/7 facility like a hotel, in Death Valley. There is one, right? Are you likely to be heating at night, even in the summer? Short answer is yes. That, or you turn off the heat and you give everybody a whole pile of blankets, right? Because it's going to be cold, but that's because the daily range is so huge. Let you wrap your head about that. So what are we doing on time? 12:35. Okay, so we've got plenty of time to get through the next point. And this is Dr. Carrier and his 3 things he figured out. Now we're going to use a really highfalutin $20 word here. How many of you have ever seen or heard of the word adiabatic? I see a few hands. Don't feel bad. So, the thing about processes in science and physics is that they all have a name by now. They're either named after some Greek or Latin derivation of what's going on, or they're named after the individual that discovered them, right? This is not an individual. This is some kind of a conglomeration of some old language. But an adiabatic process is one where you're changing state, but no new energy is being added or taken away. This is an adiabatic process. Remember we said that enthalpy follows the wet bulb line? And enthalpy is the total energy content. So if we stay on the same wet bulb or same enthalpy line, we haven't added any energy and we haven't taken any away. But if we're going from here to here, we've cooled the air off, haven't we? That looks like we took some energy away. So if we're not going to have added or taken anything away, what is offsetting this cooler, sensible temperature? It's got to equal 0. There's no new add, no, we've created nor destroyed nothing. Have we changed state? Remember when we drew the pH diagram? There. When we were doing the refrigerant thing and we had pressure and enthalpy, and we had a dome, because that's how most substances work, and over here was the difference between fully gas and just starting in here, and this is now fully liquid. That is not constant enthalpy. But if we restructured how we drew this, we could draw a process that was constant enthalpy. This is constant enthalpy. No added, no subtracted, but we've changed state. And remember, when you change from this somewhat dry air to a lot more moist air, we've taken liquid and we have moved it to vapor. And so there's a change in state, and that releases some, or that absorbs some energy. But the offset is that the latent, and this is latent, that's latent cooling. We went from this point to this point. That's a change in moisture content. That's latent heat. And we cooled it this much, however much that is. That's sensible cooling. Those offset. But if I drew this, I could draw the latent, the sensible, and I could complete the triangle. And if I did, I could figure out the sensible heat ratio. And the sensible heat ratio is this much the sensible part, over the sensible plus the latent. And if my load was 100 and the sensible was 80 and the latent was 20, what's my sensible heat ratio? What would the number be? Do the math. Oh, come on. Have I put you that far to sleep? 0.8. The sensible heat ratio, or sensible heat factor, is 0.8. And if you look at your site chart, look over here on the far upper right-hand corner. You see something about SHF or sensible heat factor or something like that, and little number lines like that? You see that thing?
Oh, yes.
That's the slope of the load. So if you started this whole process with a load calculation, and you said, I got 100 tons in this big monster train station, one big room, 100 tons. And of that 100 tons, 80 is sensible and 20 is latent. And I got a 0.8. And you started off figuring out what temperature you wanted in that room. And you'd go up here to your 0.80, and that would define the slope that you were going to move from this point that way. Now we'll talk about what that means and selecting a cooling coil. Might have time to talk a little bit about cooling coil. Now, both of these can go either direction. If I start here and I'm going straight up, what's happening?
Just lazy.
What's happening if I'm going straight up? Is somebody going to say evaporation?
Evaporation.
Thank you. We didn't add heat. We just changed. Now, you guys are accustomed to the idea that if temperatures or something else changes, there's a driver. There's a heat source or there's a cooling source. There is a source here. We haven't talked about it. It's vapor pressure. The vapor pressure of the water is always greater than the vapor pressure of the vapor. And so the water itself, internally, just it's sitting there, pressure, which there may be a vapor pressure line on your site chart and there may not. It depends on how involved they get. You don't generally need that. But the vapor pressure itself is what's driving things to move. But we're not adding or subtracting energy to the process. We just have a state that's liquid wanting to go to vapor without energy change. So, what that means in the real world what was I going to say? My brain went dead. Does anybody have a clue what I was going to say next?
Like the pressure that your temperature,
Oh, well, you reminded me.
like sea level.
So, if it goes straight up, it's evaporation. What if it goes straight down? Yeah, it is condensation. And condensation can either be because of that radiant temperature, or it can be chemical. Everybody who's ever bought a pair of binoculars or a camera opens the box and there's that little sack of desiccant stuff. That chemically is absorbing. And the line on the site chart is straight down. How about the horizontal one? We were talking about cooling it, but what if we add heat? Those lines can go either direction. Both of them. Okay, so now we get to Dr. Carrier. We'll finish with him. So there's a couple versions of this story. The one on the Carrier website doesn't exactly match what Russ Sigler told many people, or that I heard when I was back in the Carrier class. But it's close. So Dr. Carrier traveled around, and when he had his revelation, he was working for Buffalo Forge, and Buffalo Forge is in Buffalo, New York. And Buffalo, New York is not the population center of the United States, either then or now. So most of his work was Chicago or New York, maybe Boston, textile plants down in the Carolinas, Virginia. So he traveled a lot early when he was working for Buffalo Forge. And the story is, he's in this Pittsburgh train station, and I don't know if it was late at night or early in the morning, I was never clear on that, but he's looking at the railings at the train station where you wait to get on and off the cars, and of course this is outdoor climate, right? I mean, maybe it's covered in a train barn, and maybe they're driving through, so maybe you've got something overhead, but it's exposed to the atmosphere on both ends of the tunnel. So he's standing there, and he's looking at the condensation forming on the train rails. And somehow, some way, and inspiration is difficult to fully understand. I don't know how he realized this, but 3 things came out of that experience. How much of it was at that moment, and how much of it was, what he rolled through his head as he went along afterwards, I have no idea. The first thing that he realized was that for water, and he was the first to realize this. Remember I told you wet bulb had been known for 200 years before that. But he was the first one to realize that the wet bulb process with water was adiabatic. And you might think, well, so what? Well, the so what is water is the only compound for which that's true. If you were taking chemical engineering and you were looking at other compounds that exist in moisture liquid mixes, for none of them do you hit a saturation line that matches the wet bulb temperature. It's unique. So that he didn't discover wet bulb. We knew what wet bulb was. But the idea that it was adiabatic and that full saturation corresponded to the wet bulb temperature, that was the building block of the whole thing. Nobody else had figured that out. Second one. And the vapor pressure, he understood that was moving. He eventually figured out that was why. All right, what was number 2? Second thing that he recognized, which again, nobody else had recognized this before, is that for water, enthalpy and wet bulb are tied together. Now, if you were in some super duper laboratory and you could get it down to really low temperatures or really high temperatures, you could probably find it start to vary apart. But in the range that we care about for air conditioning, enthalpy and wet bulb go together. And that's why you see it that way on the site chart. And the third thing that he figured out was how to put this whole thing on a site chart so that you could use it. I will tell you that any scientist brilliant enough to have the revelation that, oh my God, water, and doing this, it's adiabatic, and the saturation point and the wet bulb are the same. That was realization 1. Okay, could an experimental physicist maybe have gotten that? Maybe. Then tying that to enthalpy, which, what the hell does this have to do with that? But he figured that out. The experimental guy might have even been able to do that. But find me the experimental physicist that could have drawn it up like this so you could use it. That's just, it's, the more you think about that, the more unlikely it seems that it could have ever happened, But it did. And that was the foundation of our industry. So that gets us through today. Tomorrow, or not tomorrow, the next Friday, we're going to do some psychometric problems. We're going to talk about cooling coils and bypass factor and some more problems. That's what we're going to do. And you'll get an idea of how people actually use that chart. Okay? Feel free to stick around and harass me if you want to. And Rich, I guess we'll end up using those pictures next time, because that'll be the first example.